Okay. So work done is K into ln 20. K is 0.5, they're given in the question, and ln 20.1. So from this, I'll get VF as something. So 4 minus ln 20.1 is VF square. Okay. Oh, ln 20 is
2 minus this.
it's 0.75 then.
Oh.
Ln 20. So 2 minus 1.5.
Oh, they're converting it to log.
No, not necessary. Okay, they're taking square root later, but they're getting 2 here, I'm getting 4.
Sir, it's half mv square, no? So 2 only will come.
No, this while doing VF, the 2 will go away. Okay, let me put the values. They got 1 as velocity, right? So this one is 0.75. So it's 4 minus 0.75. I'm not getting VF square. So 4 minus.
Okay,
0.5, 0.5, half VA square.
half mv square.
Okay, I just have ln 20, not so it's 0.75 for me. Ln 20 is 0.75. So it's I think I'm getting it. So this will be 0.75 means 3.25 VF square. In this case, VF is 1. Ah, 3. Ln 20 is 3. Ln 20 is 3. I think I made some mistake. I mean, and misunderstood what is there in the book. So 4 minus 3 is 1. So what they have written?
Very close to 1 only, sir.
I don't know what. 0.5 into something else. This should be 3, right? Only then I get 3 to 0.5 as 1.5. Okay. So
that means, yeah.
ln 20 is 3 because 3 into 0.5 is 1.5. So if you put ln 20 as 3, I'll get my answer here. So VF is 1. After that, I can find the kinetic energy. So this is the work energy theorem. So initial energy is half m VI square. Final energy is this one. And work done by this system will get added to the final energy because there is loss of energy because it's work done in overcome the friction.
So here from 2 it is decreasing, velocity is decreasing. From 0, if it goes to some velocity, now we have to add for the work done on the left hand side.
Yeah, that will be if there is no friction and there should be an applied force. Here there is no applied force, no, to give energy to this one. Just the opposing force, just the friction force. So reduce the energy. Okay. So in some sense, the work is done by the block to overcome this friction. So if you consider a system as this 1 kg block, the work is done by the system in overcome this friction. So work done by the force, by the system will get added to the right side because energy will get dissipated because of the work done. So I have to add the work done to the final energy to get the initial energy.
Okay.
concept of potential energy. Something has got potential means it has got the potential to do work. Okay, so if there's a potential in the system means it has the capability to do some work. So what is an example of potential energy? You should have known, you should know one is gravitational potential energy, right? Gravitational potential energy. So here, like, say this is Earth. So initially the mass is at some height, say initial height or lower height. If I raise the height of this mass to here, this is the final one. Okay. So here the potential of this final position is greater than the potential of the initial position. Okay. So here I can get so potential is more here, right? So if I go from this final state to the initial state, I should get some work out of it. Okay. How do I get the work done? So I just drop this mass from this height. Okay. So I can put some block here and break it. So this is the work done. Or I can think there is some air surrounding this one. So when it goes down, it will heat this air because of the friction. Okay. So heat energy is coming out. Right. So basically, this thing has got potential. I should find a way to get this energy out, get something useful done. So one thing is I can break something here, and if this friction is very, very high, the velocity here will become very, very small. So in that sense, it means that all this initial energy has gone into generating heat. But if the thing is not that high, means some final velocity will be there, say V, and the initial velocity say 0. So initial energy is mg, height of the final position or this position. Okay, that will get reduced to mg h1. This height is h1. This height is h2. This h2 plus the work done or the heat dissipated here. Okay, so here I am increasing the potential of the system by raising the height. So work is done on this mass to overcome this gravity.
This plus heat we are adding, so need not to be heat energy, it can be any energy.
Yeah, heat is also a form of energy, right? So using that heat, I can do some work. I can heat water and run a steam engine or something. What I'm saying is this final position has got more potential, right? So that means from this position, I should be able to get some work out of it.
Okay.
So okay. So now another thing is another example is spring. So spring will have a natural length. So from this natural length, if I stretch it, here the potentiality should be more. Because from this I can get the work done, I can just release it. So it'll go and hit something.
Kinetic energy will be more if we release.
Yes. Basically, I should be able to do some work from this state. So I'll release this thing and maybe make a hit some mass. Say something is here along with the spring. So I make it collide with this and break this thing. Or I can again same thing, I can heat the air here. Okay. So this potential is half k x square. Basically, x is the extension from this natural. So this is the x. At this position, x is 0. With the natural length. So this is the concept of potential. Whenever something has got potentiality means there should be some way to get some useful work out of it.
Okay.
So here they have taken the gravitational potential, which is mgh. Which is same as work energy theorem. When they say this particular case, they consider the energy as only the kinetic energy, and the other one is the gravitational potential energy, because they have taken only two things. One is the kinetic energy, and one is the potential energy, which is the gravitational potential energy. So this one.
Sir, no, sir. Don't give me vertical circular. I don't know anything from it.
No, you don't have to do anything. You just have to do the energy conservation, because vertical circular motion, the only complication is it won't be uniform speed. Speed will change. But you can forget that. Just apply the energy conservation.
Okay. A bob of mass is suspended by elation of length. imparted a horizontal velocity at the converse point E, such that it completes the semicircular trajectory in the vertical field descent. What is slack?
Slack, see, this is a support, this string is there, no? So if you are able to pull it, then the string will be tight, it will be a straight line. But at this point, okay, here there is weight mg, and there will be tension here, right? There will be a pseudo centrifugal force which is mv square by r. So it's possible that this tension can become zero. See, in this case, the tension won't be zero, because tension will be something, some value, positive. Okay, so it's possible for the tension to become zero. So at this point, the string might become loose like this. See, if you have a string and pull it, it'll be tight. This one. So at this point, it's possible that it's not tension is not sufficient, so it starts slacking. So this is a straight string. This is under some tension. So tension string like this, it's slack, where the tension is zero. Okay.
This is shown in figure 6.6. Obtain an expression for V0, speed at point B and C, ratio of kinetic energy Kb to Kc and C. Comment on the trajectory of the bob after switches. M and L.
So from here it goes up to here. Okay, they're given the figure 6.6. This one. Okay. C is the topmost point. B is this middle point. Okay. So tension becomes zero only this topmost point. Here no tension is positive. Okay. So if it becomes zero only the topmost point, then it will be able to complete the circle. Because once it reaches it, because the velocity will come here. Once it comes here, the tension will become positive.
So it won't complete the circle, it will come back to A.
No, once it reaches the topmost point, after it will complete the circle. So if it happens that the tension becomes zero only the topmost point, it will complete the circle. See, suppose it becomes zero at this point, it will stop dropping down like a projectile motion. But since it has come here, it will slightly move to this. Once it moves slightly this way, tension will start acting. Once the tension is there, you will follow this circle.
So centripetal force should be more than tension.
You can just write the expression. Okay, those things are not required for this one. You just have to write the energy conservation. Okay, C is the topmost point. Just remember that. Okay. Applying the expression for V0. So we have to find the velocity V0. So tension is becoming zero, the topmost point. So the topmost point energy will be there are a lot of things to do, right? So I should know the velocity at this point, VC. If I know this velocity at this point, there is a condition to know that velocity. Speeds at points B and C. Okay. Come up with the nature of the trajectory. After okay, to complete the circle, that's the nature of the trajectory. Distance. Okay, so if the tension becomes exactly zero at the topmost point, then the velocity is it's a known result.
That's also that known result.
Is clear. Exporting.
Something, I think two velocities would be there, root 3 GL and root 5 GL. I don't know for which I don't know.
Okay, so tension. This is the topmost point. At the topmost point, the weight will be downwards, mg, and tension will always pull. So this will be T, and the output force will be m v square by r, which is L here. So in this case, tension is becoming 0. So I have mg equal to mv square by L. Okay, from this I'll get v as root gl at this topmost point. Okay. So that's what they have done here. From this I'll get the v versus point C as square root of gl. Okay. So once I know that, I can find the rest. So what is the question? Obtain the expression of so to find V naught, which is the velocity at the bottommost point. How do you say energy conservation? So energy at the bottommost point is half m V naught square, right?
Okay, sir, wait. Root GL is the velocity at C.
That we got from this tension being 0. If tension is 0, means these two are balanced, right? mg and mv square by L. From this I get the Vs square root of gl.
Okay.
So energy at the bottommost point is half m V naught square, and energy at the topmost point is half m gl plus the potential energy, which is half m, sorry, mgh, which is 12. Correct?
So this I don't understand.
So, is it clear? It's a potential energy.
No, so why are different?
For the potential energy, I'll check this as my reference. For h, I'll take this as a reference and measure h from here. So h for this point is 0. H for this point is 12, which is the L is the length of the string. So the height of this point with respect.
Now what you're finding is energy at C, yeah?
Energy should be conserved, right? There's no dissipation. Whatever the energy at A should be same as energy at C. The energy at A is only the kinetic energy, half m V naught square. Potential energy is not there because
Half
kinetic energy half m V square. At this point, velocity is V naught. They're given in the question. This one.
Sir, but what my doubt is the full journey half mv naught square?
No. Velocity will keep on decreasing. Here will be V naught minus something. At the topmost one will be root GL. So this root GL is less than V naught. So V naught should be greater than this root GL.
Correct.
Okay.
So
here the energy is half m velocity at this point square. That is half m root GL square. So this is the energy at the topmost point. And the potential energy at this topmost point is, with this as reference, it will be mg. Height is 12. This height is 12, right? From here to here. L is the radius of the circle, length of the string. Okay.
Sir, I'm getting really confused.
No. Potential energy of this mass at this point is what? mgh, no?
Correct.
H at this point is 0 because I'm choosing this as my reference. For a height, I can choose my reference conveniently. So I don't want to complicate. I'll choose this point as my reference. So for this point, height is 2h.
2L.
Sorry, 2L. It's diameter, no?
Correct.
Which is twice the length of the string. So at the topmost point, the potential energy is mg 2L. So total energy at the top is these two terms. Energy at the bottom is only the kinetic energy. So velocity is much higher compared to this velocity, root GL. Only then it will be balanced. So from this I can find V naught. M I can cancel. So V naught equal to GL plus 2GL. So it will become 3GL square root. So V naught is square root of 3GL. Fine. I made a mistake. 2
plus 1 by 2 is 5 by 2.
Multiply by 2. 4, yeah, sorry. This is 5. So root 5 GL. Okay. Now here, V0 is root 5 GL. Okay. After that, what they asked. So it's just energy conservation only. It's not that difficult. So V0 speed at the point B and C. That is at the middle point. Speed I already found at C. That is root GL. So velocity at B. Again, you have to use the energy consumption with this point and this point. So energy at B point is half m velocity at B square plus mg, height will be L. Right. So,
அதான் sir, from there only I have doubt. MGL வந்து from B to C.
no, this is my reference always. No, I'm taking these 2 points, A and C, A and B. Energy at A, I'm equating to energy at B. I can also get energy at
Okay.
B and C. That's not required. This will be simpler if I equate A and B. The energy at all points is same, so I can equate A and B or B and C. So I'll equate A and B. So energy at A is this one, half m V0 square, and right now I know V0 from the previous calculation. That will be equal to half m velocity at B square plus the potential at point B. With this as reference, that is mg L.
Okay, I understood.
Now I can cancel them here, and then I can find. So VB will become V0 square minus 2GL equal to VB square. V0 square is 5GL, so it will become 3GL. So square root of 3GL. VB is okay. Got it? Just the energy conservation.
Yes, sir.
And then the last thing is ratio of the connectivity is B and C. Half m VB square by half m. So it's basically VB by VC whole square. VB is root 3, which is 3 by 5. Sorry, you're asking B and C. C is the top. At the topmost point, you say root GL. Here it is root 3 GL. So it's root 3 by 1 square. It will become 3 by 1. Okay. So here I have not. Okay. Only thing is to find this velocity at the topmost point corresponding to tension being equal to 0. We just have to do this one. The force at the topmost point is mg, which is vertically downwards, and this centrifugal force, which is vertically upwards, and the tension will be downwards. But since tension is 0, these two forces should be equal. So from this, I get the velocity at the topmost point. Corresponding to the condition that tension is becoming 0, the topmost point is root GL. So once I get this one, I can just do the energy conservation to get other things. Energy conservation between C and A, and then between A and B. I'll choose the reference as for the potential GS this point. That'll be convenient. Okay.
Okay.
So spring, yeah, the property of the spring is if I compress by X, the force will exert is, or the restoring force will be K into X. So this is the natural length of the spring. The force is 0 because it's not natural length, there will be any force. So now if I stretch it, you'll try to force will try to pull it back to the original position, and the amount of this force is K into X. Similarly, if I try to compress it, the force will be towards right. So you can see the force is direction opposite to the displacement direction. Here X is positive, Fs is negative because I'm choosing my positive direction as towards right. Here x is negative and fx is force is positive. So direction of the force and the displacement are opposite. That's why in the formula we have minus kx. This is the meaning of this minus. When displacement is positive, force is negative, and other way around. So if you go to minus k, this is the plot. It's a negative slope. K is positive. So it look like this. So here this is a variable force because it's a function of x. Okay. And the work done against this force or by this force is the area under the curve, which will be half into basis xm, and this value is k into xm, right? Because y value is k into x, and this value, the value of x is xm. So this height is kxm. So half into basis is half kx square. So this is basically spring potential energy.
We did potential energy for spring. This.
Yeah. Gravitational potential is mgh. Spring potential energy is half kx square. So this also I discussed while discussing SHM, right? Velocity will be velocity will be
from minus 8.
Velocity will minimum at the turning point, which is the extreme point, where the kinetic will be 0. Velocity maximum at the mean point or the equivalent mean position. Because after that, the direction of the force will oppose the motion.
It is negative.
Potential is opposite, half kx square. So potential is this one, half kx square. So it's maximum at the extreme point. Velocity will be minimum at the extreme point. This blue curve is the velocity or the kinetic energy. So it's minimum at the turning point, which is xm. Okay, you can try this example 6.8.
To simulate car accidents, auto manufacturers study the collisions of moving cars with motor spring or typical spring constants. Instead of typical simulation, the car of mass 10,000 kilos. The speed of so half mv square will be equal to half kx square.
Yeah.
Okay.
P is what?
V is 18.
You have to convert SI units, right?
18 kilometers. Oh, 18 kilometer per hour. We have to convert to meter per second.
Yeah.
Into 5 by 18.
Yeah.
Okay. Half mv square is equal to half kx square. Half kx square.
So 18 kilometers per hour will become meter to kilometer meter become 1000 and hour to this thing will become 3600. So
I directly remember it.
Yeah, fine. Yeah, if you remember, you can do it directly, or I have to convert like this. So 5 meters per second.
So in 8th grade, they just made us do this only. They will give us, we have to convert it to meter per second. They will give problems like this. Remember.
So half m is 1000, right? Into 25. That should be equal to half key is 6.25 to 6250.
25 into 10 to the power 1.
Half and half cancel. If you take the square root,
X is 20, sir.
1 0 will cancel.
No, wait. No, I'm wrong.
Take square root of 10 into 5 equal to 625 is 25 into x. So x is 2.
2 into root 5 equal to x. 2 root 10 I'm getting. No, sure. It's wrong. What did I do? 1000 into 20.
Half m v square, half m that is mass is 1000.
I'll do 7 square.
A is 6250.
6. Okay. So directly converted. Okay. 1000 into 25 is equal to 625 into 10 to the power minus 2. That will become 10 to the 1 x square. This and this will become 25. 400 is equal. I'm getting same thing only.
It's
Why
equal to
am I
2.
getting same?
Do it carefully. I think it should come.
I'm getting 2 root answer. Okay, I'll do it. I'll do it later.
Yeah,
I'll
yeah.
do it.
It's not. It's a trivial question.
I understood what to do. I'll do it.
Okay. Here is further complicated this one. So same example, we're taking the coefficient of friction mu as this one, calculate maximum compression of the spring. Okay. This is actually a good thing because previous one is just trivial thing. So now we just added some complication.
Consider example 6.8, taking the coefficient of friction mu to be 0.5. Calculate. Oh, okay. 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 What is this mu, sir? Is it mu s or mu k?
Mu k, it's moving, right?
Ah, okay, sorry. Mu k. Half k, I mean half mv square, and then mu makes it decrease. So it will be equal to mv, half mv square equal to half kx square plus mu gx.
Plus work done against friction. That is friction force is mu into n into the distance, which will be the compression amount.
Mu mg into x, sir. Okay, this will become quadratic equation.
Yes. Half m, this is 500. M is 1000, right? So 500. V is given
Into
initial velocity.
25.
That's 5. So that is 25.
500 into 25 is equal to
65.
half into 6.25 into 10 to the power 3 into x square plus 0.5 into 1000 into 10 into x.
Yeah,
Which
so you
will
can
be
solve it later because it will take time. So this is a basic equation. It's a quadratic equation. So it's being 1.35. So it should be less than the previous one because some energy is lost due to the friction, right? So
so the compression will decrease.
Previously XM was 2, I think.
Yeah. Yeah, 2.
So now this has become 1.35. This then you have to appreciate. Only then you understand the problem. Okay. Because some work done is against the friction. So the compression will be less here. Various forms of energy. This is, you already know from 9th standard. Overall, this is the easy chapter.
So this work power energy as such is okay. But in our book, there is a chapter called circular motion as such. They haven't included it in power energy.
Circular motion is one is horizontal circular motion, which is a uniform circular motion. Example is what? Horizontal circular motion.
Horizontal circular motion, this pendulum thingy.
Pendulum is vertical, right? Okay, there is one more pendulum which is horizontal. Simple pendulum is vertical.
Okay.
What is
So wait, I'll tell. Is it that compound pendulum or something?
No, conical pendulum.
Conical. This it's given in yeah.
So the same simple pendulum only, but the way you're making it move is different. You make it move in a horizontal circle. Horizontal circle. Simple pendulum, you make it move in a vertical circle. Like this and this back. This is just horizontal. So it will trace out a cone.
When it moves in vertical thing, it makes a cone.
When it makes a
horizontal,
it makes a cone. That's why it's called conical pendulum. With a horizontal circle, it will move like this. This is the string of length L. So here the velocity at any point will be same. So it's uniform circular motion. Here it's not like here the velocity will be maximum here. After they keep on decreasing, and the velocity will become 0 at the topmost point and return. Again, the maximum velocity. It's like SHM. Velocity will keep on changing. At the mean portion will be more. This is not SC, this is uniform circular motion. This is SHM. Here the tension is uniform throughout. Here the tension will be.
Tension will also be same, no, sir?
Yeah, tension in this uniform circular motion tend to be uniform. It will be same at all positions. Here the tension will be maximum at the bottommost point, T max, and at the topmost point tension will be minimum. That you can figure out if you draw the directions of the force, which is the weight and the tension, and you can put mv square by r.
Okay.
Okay, maybe I'll explain next time. So the meeting will get cut in. Actually, you can close. Okay, your mom is there.